Okay. So today's lecture is digital CAD. Probably you have seen. Again, I am telling digital circuit design, and we'll be telling that how actually CAD is related here. So mainly the in today's scenario, when we'll be doing the VLSI digital VLSI design. So CAD tool is one important thing, and that is mainly for its size. So the first point, as you are seeing, that CAD tools are introduced in the process due to its increased size and complexity. So if it is if it is a small digital design, if we give, so on the paper itself manually we can do that thing. But nowadays, that as mainly the for the complexity of the problem, and again all of you know that particularly for the advancement of the VLSI technology, that millions of transistors gates we can put in one small area, that is we are calling that IC. So then almost it is impossible to do the design manually. So for that purposes that we need a CAD tool. Okay. So we'll be seeing that how actually how we can handle, how we can use, and okay, the how we even develop that thing, what type of algorithm it is. So I will try to give an overview. Then designers want to standardize the design procedure starting from the design idea to get the design implementation, and so called the design flow. So today we will read that, say given one application, you have to say you have to synthesize, or you have to come out with a digital design. Say I want some image compression. I have an image, I want to compress that thing, that is my problem. So immediately if I ask you, you can write a C program for that. Some algorithms are available, you can write, but that is a very slow process. So for that mainly hardware is needed. So if it is some hardware is there, it will be very fast. Okay. Now for this hardware, that means we want a circuit for that. Whatever now we are writing in our first year classes the program, now we want a hardware for that, some circuit. So for that this circuit, for just now what I told, that if it is a complex algorithm, then almost it is impossible to do that thing. Then how I will say, you know, the in the C program what you do, you one algorithm is known, now you know some language, high level language like C, and you just write the program. Now similarly, that means how to enter the program, or how to represent the program, mainly C language you are using for that. So here if I want a circuit and some automated tools are there, I have to feed that these algorithm, for this algorithm I want a hardware, I want a circuit for this algorithm. So for that purposes, that actually the we need some tool. I am telling the tool that can, again that can be a software, actually that is a software. Now so probably I have some programming other than C, say just similar to C program, so that I can represent my circuit or the problem I want, the circuit I want for this problem I have mapped. Finally what is my aim? Finally aim is, again that is a software, finally my aim is I want a chip on the silicon. So just think that we are again C type of programming we are doing, that is the software. Then something, some converter I need, so that from software to even that on the silicon level I get a hardware. So these step by step, there are some different steps for this converter, from that application or the problem, given problem for representation in some language to the chip, and these steps we are calling the design flow. Okay, we will be reading in this class. Then the new CAD tools are based on hardware description language to improve the process. Just now as I mentioned that C type of language, So just remember your program, that whenever you are writing a C program, for that whatever say data type you know, actually that are not sufficient when you want to represent one circuit. That means for hardware, so C programming is not sufficient. Just think about that one flip flop you have, or some gate, even for AND or NOT gate. If I ask you to write, what you have to do, you have to that you know that what is the truth table, again some library you have to prepare, that if it is AND gate or gate, NOT gate, you will for that, or some procedure type of thing you have to write. Then every time when you will be getting, you have to go that procedure. If this is the input, what will be the output, then you are putting that thing. Instead, that if I have some ready-made thing, that I know that for this circuit I need AND or NOT, NAND gates, flip-flops, some wires, even say just think about C, there is nothing, some no representation of wire, what every time I need, or not, it is a single wire, I have multiple bus, four wires or 8 or even 32. So if I have some this type of language available on my hand, then I can write this. So again, earlier actually even 20 years before, that normally industry people when they are doing this thing, then they have different languages for them. All big companies they are doing, industries they are doing that thing. Then people have started that whether we could just like this one C is a high level language, or C++ or Java, that is standard. Then whether it is possible to standardize this type of language, and this is we call that hardware description language, HDL. So this is nothing, only to describe. Remember that this thing is only to needed to describe a circuit. Okay. So that's why the name is description language. Normally Verilog, VHDL, these are the standards nowadays. Okay. Even you could write, even 20 years before or 15 years before, people were writing themselves, and there are obviously there are different things, and they are not flexible, they are not portable, because all are different. So now that is the standard. So HDLs provide formats for representing the outputs of various design steps, and HDL based design automation tool transform for its HDL input into an HDL which contains more hardware information. It will be clear that when we will be again reading more and more. Just you summary of this thing, you remember that given a problem, I want a piece of hardware on silicon. Then first I have to do, I have to enter my, I have some algorithm for that. So I have to represent that thing. And as my aim is to get a circuit or hardware, so I will be representing that circuit using some hardware description language. But it is a software. Whatever be the thing, hardware description language, that is actually a software. So from software to hardware, finally it should be a transistor level. How I will be getting that thing? This is called the design flow. And just to represent the circuit to the to enter to some tool, it is called some hardware description language. So from HDL to the silicon chip, this is the design flow. So this roughly will be actually revise more and more. This is now I am telling, this flow will be revising. So initially the design idea means, given a problem that I have some idea. Okay, if it is a layman, he doesn't know that how to compress the image, but we know the algorithm that how to compress the image, that is my problem. So I know the algorithm, I have some hardware knowledge, I know that how to design this thing. So if it is algorithm is given, what will be the rough, that what will be the hardware, I know that's design, we call the architecture. This is the part you have to do. Only in current days, actually the first step is very important, that design idea and behavioral design. Okay, rather the tools are available, all the things the tools will be doing that thing. Okay. So then behavioral design, behavioral means just behavior of the thing. So given a problem, what will be the input, what will be the output, nothing else, one black box, some algorithm, that means what you want, if you apply this input, what output you want, that is my behavior. Just think about that, if you give this input, how we will behave, that is the function. So this behavioral design, so that means the designer, that what you are doing, you must have a thorough idea about the problem and the design, that how, what do you want. Then, so it is the flow graph or pseudocode. See, just always, because all of you know you are expert in writing C, so just think about whenever you write program, given a problem, what you do first, that either flowchart or algorithm, and then from algorithm stepwise you just map that thing to some code. So that is a flow graph or pseudocode, again you are writing there. Okay. Now instead of C, that is the hardware description now, that what type of hardware I will be using, rough, that details I am not doing, that mainly that from where to where it will communicate. Say I need a storage, I have to keep this value here, so I need a storage, from there I have to feed, I need a multiplier. Okay, so multiplier, one buffer, this type of thing I know. Then after, see, the after hardware description, there are bus and register structure. So bus and register structure means only the, here there are some buffer and where to go, the communication path, just we can think in this way. Then it comes the logic design. So now I have to see, I have this bus and register structure. So this register, mainly it is nothing but some storage, some value I have storage, somehow I have got, say some after multiplication, after division, and this thing I stored, some value is stored, and then it is flowing. Data flow means it is flowing that thing. So then the logic design is how I can synthesize or how I can get that thing, how I can represent using some get or net list, I am telling, we'll be seeing that thing. Then the physical design. So up to this part, up to logic design, we'll be telling this is the front end, as if I got some get level diagram. Now parallelly I think, just you think that if it is a small design, actually we manually do this thing, manually do. If I ask you that you design a parity generator, you don't need any CAD tool, nothing, immediately you will be using AND or gets and you will be doing that thing. So up to this part, if it is a small design, small problem, we could do manually, but now we are using, say, some hardware description and some CAD tool will be using for this. Then it is a actually physical design. Physical means actually on the silicon, if I now I want to get, because up to this I can get on my computer. Okay. Now after the physical design, this is actually the transistor layout, because finally on the silicon, how the transistor will be, when transistor is mapped. So transistor list or layout, and then manufacturing and the chip or board. So the last 3 steps, actually these are the physical design. One by one will be, this is the first level of design flow, and we will revise as we proceed. Okay, one thing, see from here, as I told that as we are proceeding, we are going nearer to hardware. That means design idea means one English type of, in English one problem is given, and then you have some idea that how what to do. Then behavioral design, if I give these inputs, I will get these output. Function, hardware description, from there just black box, block diagram, I have to do this thing, block diagram. Logic design, then how every block can be mapped to some gate using gate representation, more hardware. Logic to physical design, then we know that every gate can be synthesized by using transistor, then transistor. Then this transistor, how on the silicon that one transistor is synthesized, how it is fabricated, more hardware, silicon, finally this is a chip. So, this is called the design flow, and for these purposes nowadays we use number of CAD tools, number of software tools, because for its complexity, that is the size of the thing, it is not possible manually. Okay. Now, one by one that steps we see that behavioral representation. So, behavioral representation describes how a particular design should respond to a given set of inputs. Already I told, if I give this input, what will be the output? Just remember this thing, one black box, so this there. Now, behavior may be specified by Boolean equations. Now, I see that how technically we can represent. Tables of inputs and output values. I have a table. If I give these inputs, what will be the output? One table of input output. That is nothing but your truth table. And if truth table is there, Boolean equation you can frame. So, the first two are actually almost same, different form. Then algorithms written in standard high level. For C programming, what we do? Algorithms written in special hardware description language. So, after 1 month, you will be expert. I am telling you, say after this course, then immediately you can, now you need algorithm from there, because already we have written C program type of thing we will be doing. From there we will be doing HDL. But when you will be writing some Verilog code, so after 15-20 days what we will be doing from the algorithm to direct Verilog code, the HDL code. Okay. So, algorithms written in special hardware description language, that means pseudo code. Now, you know the pseudo code in C. Now, after 15 days you will be writing pseudo code in Verilog. I am taking very simple example. Say NPTEL is constructed by cascading in 1 bit adder. All of you know that 1 bit adder, only carry will come and then it will be there. So, 1 bit adder had two operand inputs A and B, a carry input C, a carry output and a sum output S. So, for the first bit carry input is 0, for the first there is no carry and then intermediate carries are there. And the Boolean equations that implement this function, so the S means sum is AB bar C, AB bar C bar plus A bar C bar B plus ABC. This is the, if we do the sum, we'll be knowing that this thing, this is a sum expression, and the carry out expression is AB plus AC plus BC. Now, say I'm writing some pseudo code using hardware description language. So, what I will be writing? This is a module carry. Okay, so I have two equations, two expressions, one sum, one carry output. For each module, one sum and one carry output. 1 bit, 1 plus 1, 0, carry 1, sum 0, carry 1, 1 plus 0, sum 1, carry 0. So, this type of thing. So, if I think that this is a module, then it has two output. Okay. So, the two expressions we have given. So, module carry, that is this, I have written CO ABC. So, CO means that is my output, carry output, ABC are my inputs, AB are the two operands and C is the carry in. Output CO, C I have defined just like your C language, output CO, input ABC, assign CO is equal to A and B or A and C or B and C, that means A B plus BC plus CA in module. See, just similar to your function writing. Then to specify the timing behavior of the gate. Now, what was not there in the C programming, that there we don't need any clock or how that it is simulating, how the circuit is behaving, because you are mainly simulating on software. Now we need that exact some physical parameters. Now see that how we give the some delay or some time to specify the timing behavior of the gate. See the same thing we have done, only where some I have given where hash 10 then CO equal to. What it means, this hash means always you will be learning that thing very long, or some of you must may be knowing that this is actually the delay, some time I am giving. So at time unit, at 10 time unit, this hash 10, so whenever we will be writing some unit we will be defining. So this picosecond, nanosecond, something will be defined, some hash defined. Then this is with this 10 unit, after 10 unit only this your carry output is available. Because now you think you want some hardware, so and hardware means whatever small delay it is, some AND gate has some delay. Every that AB plus BC plus CA means you have 3 AND gates, 3 2 input AND gates, but all can be parallel, and one 2 input AND gates, 3 2 input AND gates, and one 3 input OR gate. Again, whatever less it is, it has some delay. So total carry module, it will be some delay. So it has some delay. So when the input you are applying and when you will be getting the output, some delay of that module will be there. So mainly just I am incorporating that thing, because now you think if my module is a bigger one, and if I there now for large circuit what will happen, it is module wise. You remember that it was the first that block I told. Now that one block, that it has some delay, and if you don't consider that thing, then if the output of the first block is the input of the second one, then obviously there will be a mismatch if I don't exactly give the time which must be greater than equal to the delay of the first block. So when it will arrive on the second input, it will be a problem and your everything will be a mess. So this is now all these things are very important. And now think the programming, you know, the C programming type, there all these facilities are not there. Probably you could do, but for that again you have to write a program. You have to write a program so that you can incorporate. It is possible, but if every time we need that thing, so whether all these facilities are there. So actually hardware description language is nothing but a language which provides all these facilities that which are available, which are we require for this hardware design. Okay. See, I can represent in this way. As I told that behavior I can give in a different ways. So see that this is the truth table, nothing but the truth table. So ABC, there are 3 inputs and carry out. Then just think that 1 1, if it is 0 or 1, 1 1 0 and 1 1 1, the carry out is 1. So that's why question mark means it is actually don't care, 0 or 1. Similarly, this is 1 0 1. Similarly, it is 1, whether it is 1 or 0. So actually this is nothing but all possible combinations of inputs. This is my truth table. So the table format I can give. So this is another way. Some primitive carry, again the same thing, output CO, input ABC, and this is a table, and then N table and N primitive. In this way also you can give your behavior. Okay. And expressions also you can give, later we will be seeing. Now this is a structural representation. So we are seeing that one by one, that boxes of that flow. So structural representation specifies how components are interconnected to perform a certain function or achieve a designated behavior. So the first, you want this behavior. Okay. If you want some given problem, you want, if I give this input, I want this output. If I give this set of inputs, I want this set of outputs. That is the behavior. Now you have to map that thing to a structure. Structure means that can be gate, some module. You say and is a, will be telling, and or not, these are some gates, and then and or inverter together I can tell AOI. module. Many times nowadays it is called it's a gate. Actually this is a AND or two input AND, two input AND, one OR, one inverter, AOI, OAI. All these things are actually very much used in designs. So this can be a module level. So how I can map now these functions, how I can map to these modules or gates. So this is my structure. Now some architecture is coming into picture. So in general the description of the list of modules and their interconnects often called net list. So this is very important. In your now your digital design often we will be using the term the net list. So net list is nothing but the description so that the how modules are connected. Remember many times now onwards we will be using the term. So how these modules, how they are connected. Okay. So the module level, gate level, switch level or circuit level will be seeing. See this is a 4-bit adder. Okay. So 4-bit adder I can take 4 1-bit adder. I don't know whether they will test it. See, I have oh, sorry. I forgot. See, I have a number A which is 1011. This is a 4-bit number. I have another operand B, say which is 1001. Okay. So if I add, what will happen? So I have 4-bit. So this is the first bit 1 plus 1 0 carry 1. So actually for the first module, this is one output. This is one output. Some say this is my S1 and this is my carry out CO1. Similarly, now for the second module, and see here carry in is for this module the carry in is actually 0. C in is 0 for the first module. For the second 1-bit adder, these are A is 1, B is 0 and this is my carry in C, that is 1. So this is 1 plus 1 plus 0, so 0 again carry. So actually I need a 4 1-bit adder. Okay. So if I say this is, and for every adder, so there are 2 output bits, sum and carry, sum and carry, sum and carry in this way. Okay. So I'm just taking one simple example and how actually as if hierarchically we are designing. And see this, what is this module? What is this one? AB plus BC plus CA, 3 and 1 OR. So this is actually the carry module. Okay. Now if I write 4-bit adder, so this is my root module. This is my this module at 4. So module at 4, sum C4 CI AB. C4 is the final carry out, carry in, AB is the operand. Now my AB, see for the 4-bit adder, my AB are 4-bit value, 1011 and 1001, just now the example we have taken. A is 1001. So for that, say what we have done, that input 30 AB, just like your array. See that in your C programming, that array you do, and actually this is almost the same type of structure for 4-bit value. So if in your C program, if you want to do using C, actually you need a 4-bit array. So that is similar type of thing they have done. It is this type of syntax is available in. So this is a 4 bit. Then say input is Ci. That means unless it is it is specifically told, it is only 1 bit. Okay. Then output is again 4 bit because my sum should be 4 bit. Again output C4, that is the final carry. That is the final carry. So again if we take the example, then it is 1, again carry 0, and 1 plus 1 0, carry 1. So actually this is my C4, this is my C4, and this 0 1 0 0, this is my S, this is my 4 bit and this is my S. So now see, this is a where, say this is where 220 means 3 bit carry out. Okay, because C4 final carry I have taken as separately. Now see the 1 bit adder, this is these module, these are all 1 bit adder. So this 1 bit adder, it is written add A0, add A1, add A2, A3, and see 1 bit adder, there are C00, S0, these the first two are the output. Normally this is the way we write, the first two are the outputs and the last three that they are the inputs. See for the first module, this is the carry in Ci, A0, B0, then carry out and sum. Then second module, this is carry out 1 and sum 1, these are the two operands, and this is the first intermediate carry output. Then second intermediate carry output, actually these are the third bit and these are the fourth bit, and final carry out is C4. This is the simple thing I told, so that the one large circuit from here, finally our VLSI circuits, VLSI digital circuits are large nowadays. So these can be partitioned into some modules, and as if one module, the way we have given one module, we can directly or separately we can write, and then how to add that thing together. So this is the one simple thing we have taken, and as if this is the modular design. This is the way we do. See, so obviously we have to know the addition procedure. That means we must know the algorithm that we want to implement. Okay, the design idea that you have, the behavior that you have. So the first two steps are the important thing. The remaining things actually will be that your tools will be doing. See, these are the three intermediate carries, because there are 3 bit. For last one I have taken as a C4 separately. That's why it is not 4 bit. This is the 3 bit. That this is the where. Again, this is where means as if just you can think as if the always 220 means you just think that there are 3 bus. Okay, 3 line bus, and that you are using for the carry out. That see, your one is C00, C01 and C02, these are the 3, C00, C01 and C02, so that is why it is 3. See the code, these are 3 only, okay. That is why it is 3 lines are there. So it is where is defined. So actually hardware description language, all this syntax, normally what we use in the hardware, that all the things are already defined, predefined. Okay. See, now we can write in this way. So module add, again carry and sum, 3 inputs ABC. Now say module wise I am writing sum S1, carry C1, N module. So this is the way you have to attach. Exact Verilog code you will be reading later, I think today or just after this class. But this is the pseudo code of hardware, pseudo hardware code. Again here see that where XYZ. So XYZ, these are the WAC type, and as this is not given, bus structure is not given, that means it is a single wire, single line. Okay. Okay, now the physical representation. So up to this actually the front end. So in an IC process, the lowest level of physical specification is photomask information. Okay, actually, just I'm giving one idea. Probably it will not be very clear at this stage. Say, finally, you want on a silicon the some transistors, some gate level design. Every gate is can be represented by a number of transistors. So finally, these are connections of transistors. So on the silicon where the transistors will be there. Again transistors, I think you have read your design, that digital design electronics course, that what is actually a transistor? What is a transistor in that that PNP transistor, how it is represented on a silicon? Hmm? Diffusion and polysilicon, if two crosses, one transistor will be made. So finally on the silicon, actually it is nothing but a map. See the polysilicon and diffusion, how it will be there. So for this flow design what we have read, finally it is nothing but a one file will be generated which will give the photomask, that means mainly the position of the transistors. That means what will, how the polysilicon layer and the diffusion layer is crossing, only this mask will be going. So after this flow design, you will be generating one file which will layout file that you will be giving in the fab lab, the fabrication lab. They will be what we will provide, that it is nothing but a file, and that is a photomask file. I think it will be later, this is, it will not be so clear now. Okay. Now again we revise the flow. So see that this is the um, design entry, means now we know the hardware description language, how to write the modular wise will be writing. So in this Verilog the design entry we have done. Then it is a logic synthesis. See, gate level from there, how the gate level circuit is coming, that we are calling, that is the logic. Again I will explain that thing. And now it will be a, see this I have read, I have written logical design or the front end CAD. So actually this portion, after you enter your design on some using some hardware description language like Verilog or VHDL, this synthesis part, some CAD tool is available for that. That means some software is available for that, you have to use, because it's a, now it is a very large thing, we cannot do manually. Okay. But the just now what I told, that in this way, that the program, the Verilog code you have written, from there how the gates you are getting. Then it's a pre-layout simulation, means whatever now you have got, given a problem, you have some algorithm you have applied, for that algorithm what type of design, from there you have got some gate level circuits. So now you are simulating whether, because you have the behavioral design. So now you are simulating the circuit you have got, whether the same set of inputs is giving the same that output or not. So this is one type of verification, that whether actually you are getting or not. See, your design entry or your Verilog code is nothing, it is only describing your circuits. That is why hardware description language. Even when you will run, you will be seeing that there is no error, that type of result is coming, nothing else. So just to verify, again you have to write some test bench separately. That means you have to give some input, and for that input what output is coming, that forcefully manually you have to embed on that. But only HDL code, only it is the description, that how actually, I know I have some English type of language. In English I know that this is my problem, this is the solution procedure algorithm. But how I can map to this my hardware, for that actually we are taking help of HDL, nothing else. Okay. Then you have to give, that we call the test bench thing, that you have to give that this input if we apply, then what will be the output. Okay, so up to this blue one, that logical design front end CAD, we call this is a front end. For that, front end CAD tools are available that you will be learning in your lab classes. And see, now next part is actually the VLSI, we call the physical design. Actually on the physically on the silicon, how we will be getting, okay, you have got some circuits, some simulation it is giving. Now on the piece of silicon, how we will be getting that thing. So this, for this we need a floor planning, placement and routing. These are the main 3 steps. See, you have some silicon, you want that this, I want that okay, 3 centimeter by 2 centimeter chip. So this is your floor plan, this you are giving, on that I want that thing. Then placement, then your large circuit, you know the how you have to partition, so that where I will put that thing, so that my interconnection will be minimum, my routing will be, that path will be minimum, my clock, there are many things that you will be learning, that your clock will be, because I told that it will be a mismatch if the clock mismatches, the output will be a different thing. So how it will be placed, so that my area constraint is satisfied, what 3 by 2 centimeter square, that 3 centimeter by 2 centimeter I have given, then everything will be satisfied. So this is a placement. There are many other objective. And routing, again, how I will, because within this small area, see, so many millions of wires will be going. So how we have to route. Finally, the objective is actually routing. That means that mainly the 3 things we will be seeing. One is area, one is delay, the time, another is cost. So power, now it is actually physically I should tell area, delay, power, and obviously these are the cost function. So these are the 3 things of physical design. See, now again circuit extraction I will be doing, because now you have everything, you have done something. Finally, within this small area you have got some circuit. How do you know whether it is the thing, the circuit, same circuit what you wanted? So again from there you have to extract the circuit, you have to do the simulation. That means again it is a verification, that what exactly you wanted, what you were getting that thing on your silicon or not. Then if it is okay, if it matches, then you get a photo mask of that thing, what he told, that finally the transistor to that polysilicon and diffusion layer or that metal contact, all these things, then one mask. So finally it is nothing but a just one graph paper, you think that position x axis, y axis, where that this thing is there, this type of file it will generate. So on the silicon it will be actually pasted, and again another electronics, the device level thing will be coming. Just again summarize. So behavioral description, design idea, that is the main thing. Again I am repeating, because what you have to do, that all these things you have to know, so that as if this is a back annotation type, you have to know all this design flow, so that you efficiently write your code. So first thing you have to do, the design idea, that how you will map, that is your thing. Then behavioral description, that is also yours, that how using HTL code, using Verilog, that always at beginning, this is the thing I am telling, the code, that how you are getting. Then this is a modular description, again okay, now you write this modular description. Then logic design from this module, as if every module is mapped to some number of gates, every module, gates and for sequential circuits, flip-flops. Then transistor level, every gate is that can be synthesized by number of transistors. Then this is on a IC. So these are actually logic design and physical design. So here, say even we are writing this thing, so modular description, that means a good designer should have some idea about the module also. Then it will be, because this is one thing, if we see that given a problem, that if some students starts writing on the Verilog code directly, he think he is very smart, he or she, that okay, but that is not the, actually that is not at all a procedure. Then immediately we tell that you are a bad designer, because unless you know the modular structure, always I'm again telling, every year I tell, but very few students they actually follow, that whenever a problem is given, you want to design, first you do a paper design. Paper, on the paper you write that this is the algorithm and this design idea. I told that is the thing, that first you draw this is the way I can do this thing. So this modular description, actually good designer he has this thing. Then as it again see, as if some in the from the bottom up approach we are doing, as if from here I am writing the code. These two together, though in the flow we tell this thing, but unless if it is there, then actually it will be very good, particularly for debugging, because it's a large code. Normally it's a huge code for big design. It's a very difficult for the design, and every steps you have to simulate. As I told that at least 2, but there are many other steps also that you can verify your thing, then it will be a problem. Okay. So always you start with a paper design, my suggestion. Otherwise it is not possible. Then probably for this course it is okay, but never you will be a good designer. It is not possible at all, and debugging is not possible. Okay. So now this is the flow, and now how we nowadays what are the technology normally we use for making a chip. Okay. So this is now VLSI design styles. Okay, programmable logic devices, standard cell based design and full custom design. The last two actually you will be doing in VLSI lab. Then you will be asking why you have written the first one. But nowadays the state of the art, or that is also state of the art, but what I tell that this most popular, handy, even you can buy, immediately you can do, that's the programmable logic devices. So that's why the first I have kept that thing. But in this particular lab, this course, mainly you will be learning the last two, standard cell based design and full custom design. Who will be doing digital, they will be doing the standard cell based design, who will be doing the analog, the full custom design. But this programmable logic device, now it is, that is the scene. That's why I kept that thing, because you must know, if you are doing very VLSI course, you must know that that is there. And I think in our institute, the computer science, electrical and electronics, all 3 department, almost every lab it is there. So you can use that thing, no problem. And design flow is same. Okay. So programmable logic devices, I have taken this thing from net. So you can see, you can explore. So they are actually the logics that mainly we have partitioned into 2 types. One is standard logic and ASIC. That means the application specific integrated circuit. So logic means standard logic, there are already some things available, we will be reusing that thing. Just one simple example I am giving, for whatever be the design, I need AND or NAND flip-flops. So if I have that type of library, then immediately I can use that thing. A or C program, always printf and scanf, it is there, you just using. Actually library it is given, because every time we need scanf and printf. The same concept, here only some hardware module. And this application specific, so it is not there, only give one algorithm that say you are proposing, now you want to measure the performance or you want a chip, then that is there. Now these, as for this ASIC, say programmable logic devices, gate arrays, cell based ICs and full custom ICs. So mainly these cell based ICs and full custom ICs that you will be doing here, and these gate arrays etc., what probably many of you have listened, the term is Fpga, mainly in the current days, but actually this is a programmable gate array, one type. So these are your PLDs, and there are different. See here I have given actually programmable logic devices, SPLDs, the PAL, CPLDs, complex, FPGAs, and mainly current days this is the thing. But one good thing is the flow is same. Only after that where you are actually downloading. This is there. Okay. Okay, these common resources are configurable logic blocks, memory lookup table, and or plain simple gates. This is for the programmable part, the programmable logic device. Okay, I'll be telling that thing. So quickly we tell the FPGA, because for this class I think in the lab you will be using the CMOS. So that's why FPGA is not the thing, but still I am telling. The field programmable gate arrays, this is an array of logic cells connected via routing channels. So thing is just summary if I do, as if the hardware is there, it is available. FPGA means that actually the chip is there and it is, as its name, it is programmable. That means depending on your circuit, as if it is that can be programmed. So immediately, if once the software part means tool part, the design flow part is over, within 2-3 minutes you will be getting a chip, and it is very cheap also, means cost. So that's why nowadays it is so popular. As I told that in all our 3 departments, it is almost every lab you will be getting. Okay. So okay, this I'm giving one structure. I think this is the main structure. You can get this thing. So it has that a configuration logic block, the CLB, and this is actually the concept switch matrix, because it is programmable means what? It can switch that which CLB to CLB it will be going. Another thing is another very the basic concept I am telling, if some of you use later. See, whatever be the behavior, mainly some behavior or function, every function I can think, or many of you I think, at least computer science people, they have read that every function we can use that using memory. I think electronics also there are some classes that some memory, using memory you can design any digital design, mainly multiplexer based design and memory based design, that type of thing. So here you will be seeing that actually FPGA is nothing but that lookup table, LUT, you will be so lookup table is nothing but a memory. Think that my behavior is this as if it is a table, if this is the input, this is my output. So whatever be the thing, whatever expression, Boolean expression, everything always I can keep represent like this, and actually FPGA has done that thing. So everything is written there, and now depending on your requirement, it is just switching that thing. This is the idea. I am not telling much more. I think design flow is same. Again, mainly we use Xilinx and Altera. So design entry, see the same type of design flow. Design entry, and this is in VHDL Verilog, and you will be using the cadence, mentor, etc. implementation, and then download on the Xilinx. As everything is over, the up to the design flow, actually within 2 minutes you will be getting. So this type of board, now you see, you go to your lab and you see that this type of boards are available. Actually chips are there, all the hardware is there, and only this flow, design flow, that you will be learning. Just we have started this thing, the Verilog code you write, the CAD flow, the CAD tool you run, you will be getting finally the layout. Only the last layout will be different from the CMOS and here, because here already it is a, what it will do, it will be giving you a layout that how it will be switching and what type of, what CLB it will be choosing. So that only that layout you will map to this, you will map to this board, this one. Okay. And CMOS will be seeing actually that the photo mask of that polysilicon. Only that last thing is different, because the technology is different. I think I just am skipping. It is there. So if you are So now it is standard cell based design, what you actually will be using. See, there are two type of design, normally called digital and analog. So how actually it is coming, what is the difference that I am telling? One is, this is the standard cell based design. So one of the most prevalent custom design, also called semi-custom design style, requires development of a full custom mask set. Basic idea is all of the commonly used logic cells are developed, characterized and stored in a standard cell library. Just I told, very simple way thing. Whatever logic cells and or not NAND, even some bigger modules AOI or OAI, as if everything is already prepared, tested, module wise, some in a library it is kept. Now depending on my design, whatever is needed, I will be taking from there and I will prepare my thing, reuse. Okay. Now just be clear, when you will be working in this lab, you will be seeing that we are using National Semiconductors lab. We have some agreement. So actually this National Semiconductor, they have one fab lab, because we don't have any fab lab. Not here, even not, okay, some not that good lab in say our Kharagpur. So what they are doing, see the fab lab actually on the silicon, what transistor you are putting there. Now you know, now you remember your previous thing, every transistor has some that L by W ratio, what is length, what is W, and the way you are simulating your thing on the software, if it does not match with the same L by W, everything will be a mess. So if I actually work, if you don't want a silicon, no need, up to anything you just simulate. If you want only, you want to learn up to front end, actually you don't need. You just use your cadence or synopsis tool, and then there they have given some library. Using that library you synthesis, no problem. Actually there are some libraries there. If you use synopsis, they have some simple library, not so sophisticated, just for your purposes, learning, etc. it is there. But finally if I want a chip, so the AND gate I am using, and the AND gate that can be replaced by some transistor, finally AND gate is synthesized by some transistor, the LW of that transistor must be the same as that what in the fab lab, that fab lab I will be using, because otherwise the LW is different, everything will be different. Clear? So actually National Semiconductor has given that library here. So when you will be, you must be very, just for first 2-3 days you will be facing the problem. Some people you will be seeing that it is working nicely, some people nothing coming, because their library is not, the path setup, normally the problem is path setup is not there, because all of your accounts are new. So unless the library is accessible from your directory, you will be facing that it is not coming. Okay. So all this, what is this thing, that actually national library, that what they provided, that is, that must be set, that from your directory it is accessible. Okay. So using that library actually you are simulating. Okay. So this is the standard cell based design, that all the standard cell that are already made, tested, and it is given to you. So that library they have provided us, and that is a big thing. Okay. And that is actually, so now you will be seeing that we are using 0.1, I think now it is 0.13, 0.18 earlier, 0.18 micron technology, 0.13 micron technology. What is that? We use that thing, and when in the Viva we ask the question, and the student they don't take. So what is 0.18? So what is this? This is channel length, half of the channel length. Actually feature is defined not the half of the channel, lambda. Lambda is half of the channel length. So this is 0.18. Now again, as the technology is advances, it is 0.13. Now think that actually National Semiconductors lab, fab lab, they are using that 0.13 physically, and that library is given. Unless that library is given, say earlier we had 1.18 micron technology, library. So if we simulate in our that using CAD tool, we simulate 0.18 micron and we give it to 0.13 micron, it will not work. Everything is a mess. Okay, so that is very important. So that everything is given there. See that I have actually it is written that the inverter can have standard size, double size, quadruple size, and see in the library if you if some of you have interest or after when you at the last phase of your course, if you ask some research scholars or the seniors, they will be showing you that actually in the library you will be seeing even the inverter that 3 inverters are available, because depending on my design sometimes inverter we use just like a buffer. That means I want to insert a delay in my circuit. So how I can insert a delay? I can put 2 AND gate. I can put say 2 NAND gate like this. Sorry, this is the sorry. I am telling 2 inverter. Say this is A, this is A bar, this is again A. So these 2 inverter, just I can treat this thing as nothing but a delay. Okay, just I put that thing as a delay. Now, depending on the L by W of this transistor, I think you can remember in CMOS what is the circuit of CMOS? Sorry, this is so. This is my NMOS, this is my PMOS, okay. So now see this transistor, if the L by W, if it changes, the delay will change. So because it is transistor, so now this buffer module, that means if we choose a different inverter or different transistor, different inverter means different transistor, and then the delay will be different. Okay, so depending on your application, actually that whether standard size transistor, double size transistor or quadruple size transistor, that what you will be taking, actually it depends on that, and you will be seeing that actually in your library all these different type of transistors are available. Okay, sometimes you can ask your seniors and they will be showing you. The chip designers can choose the proper size to achieve high circuit speed and layout density. So this is your task. Depending on your application, if you want more delay, you will be choosing a different type of transistor. Actually, you will not choosing transistor, you will be choosing an inverter, the NOT gate. Now each cell is designed with a fixed height. So to enable automated placement of the cells, now I told that okay, now as if transistor etc. you have selected the physical design, that first thing is a floor plan, placement and layout. So in the placement, because floor plan means already you have given with this approximate area I want my full circuit, this chip size should be this, then you have to place properly. So to enable automated placement of the cells and routing inter-cells connections, a number of cells can be abated side by side to form rows. I am showing. So. See, these are the things. I think one better. See this thing. See, this is the way. See the rows, and see there are some gaps here. So actually within this is called standard cell row. So whatever you have selected, actually within that row it is placed, and this gap area is actually for the routing channel. Okay, so see the way it is written, some row, again some space for routing channel, again some rows, and within that rows actually your cells are placed. and this is for your IO padding. These are that boundary, these are for all your IO pads, okay, input output. So this is actually given there. Okay. And now, okay, one by one you will be seeing that thing. So the power and ground rails typically run parallel to the upper and lower boundaries of the cell. See, these are the parallelly are going, that is the power and ground. And neighboring cells share a common power and ground bus, and NMOS transistors are located closer to ground rail while the PMOS transistors are placed closer to power cell. Now whatever you have read in your theory, now you will be seeing actually accordingly it has been done, and actually whatever you have read in your theory, that is implemented in the CAD tool. So CAD tools are nothing but theory you have read, that somewhere are actually written program and automated, some tool they have prepared. Okay. For this floor plan placement and routing, actually a number of good algorithms are available. So these tools are nothing but the implementation of those algorithms. So floor plan for standard cells. So inside the IO frame, which is reserved for IO cells, the chip area contains rows or columns of the standard cells. I think the figure you can remember. And over the cell routing is also possible. Actually there are different type of routings are possible. Why I am telling, because if the physical design when you will be doing, many times you will be seeing that there are errors, and that time that even changing something, it is not possible to debug, that time manually you have to do. Okay. So that time you come back and read the slides, okay, and where it will be the problem, because manually you have to put that thing. So after chip logic design is done using standard cell library, the most challenging task is to place individual cells into rows. As I told, remember the flow, that once the cell, so as if library, all the logic cells are there. So now when you are synthesizing, they are taking from the library that whatever cells are available. So that available cells, with the available cells, they are making the design. Once it is done, then the is to place individual cells into rows, because already the floor planning is there. So you know that these many rows are available for putting the cells, and this is my routing channel, that what space is available. Then interconnect them in a way that meets the stringent design goals. Circuit, chip and power, all are contradictory. You will be seeing that if area you want to reduce, always obviously I want to reduce the area, then it will actually affect the power. There are many other issues also that some other course you will be reading, that if it is very less, then power will be more, that it becomes hot, the chip, many times we have seen our practical experience. Then speed is a big problem, and many other things are there. So many advanced CAD tools for place and route have been developed and used to. So one thing you know, that these CAD tools, whatever you will be using, this is not very special thing. You have actually, you could design that thing. These are number of algorithms are available. Actually they have done these algorithms, they have implemented. For placement, and good algorithms are there that they have implemented, some good user friendly, that GUI they have provided, and that's why, nothing, otherwise not. Okay, this is mainly semi-custom is what actually we have told, that is for the digital design we need. For the digital design, actually this semi-custom thing is possible. That means library and or not NAND gate with their delay, that for a particular LYW ratio, what will be the delay with all characteristics as if the library is available, and that library must match with my fab lab, what actually I will be doing in my fabrication lab. So using that thing I am synthesizing my circuit. That is the summary. Now, so it is written the standard cells based design is often called semi-custom design. Semi-custom why? Because cells are available. So now depending on your application, application is new, that is now as if you are choosing the cells what is available or what is for some fab lab, that fab lab you will be using. In the full custom design, the entire mux design is done anew without using of any library. Normally the analog circuits we do that, actually you have to design a transistor. You will be seeing from the from the circuit is actually from using the transistor level diagram. All the transistors are there. So everything you have to do. What you can do, that what will be the transistors LW ratio, everything that you are doing. So that it takes much larger time than digital. Okay, so the development cost of such design style is prohibitively high. The concept of design reuse is becoming popular in order to reduce design cycle time and cost. So actually for digital it is nothing but reuse. Even for this stage VLSI design, we are telling reusing cells. Even nowadays this is also not actually reuse of chip, we call core. That it is mainly the all core, one processor is available, take the processor, put that thing and do the design. This is all core based design called system on chip. So nowadays even it is more, but for analog it is actually difficult. But even for analog circuits now people are trying to at least develop some library, but though it is very difficult. So the most rigorous full custom design can be the design of a memory cell. You can try. I am giving one problem. I am giving because normally your seniors they will not do this thing. So if possible you do that thing for a memory. If you do for one small memory, actually if I think some of you must know the memory design, or it will be actually repetition, but actually it is a very good task for the analog, and some mixed digital and analog both. So you can try this thing. Since the same layout design is replicated, I have told there would not be any alternative to high density memory chip design. Actually it is not there in our lab, so that's why it's a limitation. You can think. Okay. So for logic chip design, a good compromise can be achieved by using a combination of different design styles on the same chip: standard cell, data path cells and PLS. Okay. Sometimes people do this thing. So in real full custom layout, geometry, there is some values. I think these values you forget because slightly older. Every day it is changing almost. Okay, just forget about this thing. Here are some comparison is there. You read, this is not a big thing. The other I tell another thing. Okay. So whatever we have read now, this is a very common picture. It is called Y diagram. See, this is the we have read now: behavioral, structural. Finally, I want a physical thing. Behavioral means those who are lazy only knows the behavior, give the thing. This is the inputs, this is the outputs, function. Structural, those who are expert wants a very good design, particularly once his design must be synthesized or he or she gets a chip. So structural thing will be doing, and then so more abstract design, and finally this is the physical. So behavioral, from behavioral you can synthesis to structural, remember your flow, then physical design. Okay. So now I give what actually behavioral means: algorithm or flowchart. Lazy people only know the algorithm, this is the thing, this is the thing I'll be doing. Again for them also something is available. Okay. So processor and memory, but I have more idea, I am design expert. I know the, as I told you, that you start with a paper design. That means you know that where the processor is needed, memory, register, the whole connection block diagram level. So this structure, then PCBs. Okay. MEMS etc. physical thing. Then register or transfer, people can start from here, that also a behavioral. Register multiplexer, ALU, multiplexer based design or ALU etc. Then ASICs or FPGAs, okay. Then it is also physical. Boolean equations can be the behavior, gates or flip flops, logic gates, then cells. Actually the CAD tool you will be using, it will be giving, you can give your Boolean equations. Initially you do this, initially small things you take adder, 8-bit adder, take multiplier, I think they will be giving some decoder, okay. Then this type of circuit you take and do in this way. Then you will be seeing after logic design, you will be seeing that some gate level design you have got. You can see that some options are there, you will be seeing that thing. Then okay, transistor function, transistor layout. So issues in high level synthesis. I think I have told only circuit theory, just think transistor, capacitor, resistors are available. Physical design only wire segments and vias, as I told, polysilicon and diffusion, layer and butting contact, metal, where is the connection. So the via, the hole. So these three are only physical. Logic synthesis deals with 3 Boolean operations and non-not and the sequential circuits, deep flip flops. HLS deals with many ALUs, shifter, buses, signals, high level, this is the high level synthesis. Forms, register transfer logic, forms form memories, processor, controllers and arbiters. So it is up to you that depending on your level from where to start, where you will be doing, so it will be giving in this way. Okay, description of system components, information needed to define system components. I think you can read this question. Again revision of the design flow. I told the first one I have given. Now again we are reading and we are coming more. Say this is the RTL specification or Boolean equations, means that this given in Verilog code. Then it is the logic synthesis, see schematic capture or logic verification. That means all three people can do. A good designer will be doing, he will be synthesizing, schematic capture will be taken. Schematic capture means that the circuit level diagram, okay. Then logic verification, that means what given the problem, whether at all you are getting the solution or not, correct solution. Then it is technology mapping, means just now I told for digital circuit design, this is the cell library. So this is called the technology mapping. That means actual technology is coming there. What is used in the fab lab, that is given as a library in your lab, that you are taking when you are synthesizing. So this is actually technology mapping. And that in the library, actually that what is the size of the transistor, what will be the delay, what area it takes, everything is given with the characteristics of the library. Okay. Accordingly you are choosing, as I told that if you want a delay, you want to use a inverter as the delay block, then obviously the different type of transistor you will be choosing. And if you want it should act as an inverter, then it will be a different thing. Then logic simulation. Okay, this are some stimulus, means that test bench you are giving some input, and then again component library I need for this simulation, and see it is giving your physical design. So all these things are the front end actually. Then you will be, and what is this back annotation means? That means every time you have to actually go back to your design and you have to change. Okay, every step you are doing this thing. And see this logic verification, many steps you will be seeing there, you will be probably you will be using a different type. Initially you don't need, but later when you will be become expert, you must use the verification tool also. In our lab it is there, some Vera. So at every step I also told you after front end, and then after every step that you must extract circuit. When the layout is, even you get the layout, that time also you have to check whether actually it is getting, because once you get the circuit on a chip, it is very costly. CMOS is very costly. Why FPGA is so popular now? Mainly cost is one parameter. Okay. So that's why you must be very sure that every step you are getting the correct circuit. Okay. So these are the how synthesis is defined. Is a process to convert a circuit description written in HDL. So this is your Verilog code. From there you are getting this type of circuit, and when this type of circuit you are getting, that circuit is actually synthesized by the transistor that is available on your netlist, your library. Okay. Now sometimes optimization, you will be seeing that optimization. This is one. I am just mentioning what are the very important thing. Say you have given some circuit, and when after simulation or logic synthesis you are getting a different thing, because every time the tools are written that they optimize that thing. So be careful about that thing. So consider the following equation, say C and C1, this type of logic, and if it is out, so you will be getting, after optimization you will be getting this type of circuit. It is nothing but a AND gate. Okay, probably you have done so many things, C, D, C1, D equal to C, out D, then you are seeing that it is nothing but a 2-input AND gate. Okay. So tools are like that. Then schematic capture, that graphical representation of a netlist of components. Now it is difficult, but sometimes we use that thing, it is necessary. Okay. Sometimes it is not possible for us, is a huge thing, or someone has given me the circuit, so scan it and put. Okay. So netlist, just I have given some options, so that if you read see this type of file available. So these are the schematic, and netlists are, say this is a 2-input NAND gate, and then normally these are normally these 1, 2, 3, one is the output. So that means every output and input, all the lines have some marking, and accordingly you give that these are 2-input NAND gate, then two are inputs and one is the output, and in this way you just say, if you give this is 1, 2, so for this NAND gate this is 1, 2, 3, then again it is 1, 3, 4. Okay, in this way this is 1, this is 3, so 1, 3, 4, this is 2, 3, 5. Okay, then 4, 5, 6, in this way it is written. So that is a netlist. Okay, these are some logic simulation, and so for simulation the behavior of components that are already available from component library. So according to the library, actually it is giving the thing. Ability to handle large circuits, so these are the things, and these are the simulation objectives. The functional correctness of the netlist, as I told, every time it is necessary. Timing analysis, that estimation of delay, critical path, hazards, recess, particularly for sequential circuits, because finally delay is one thing, that with what clock your chip is working, that is the thing people will need. And the test generation required for manufacturing test to be discussed. Okay. Testing will be, you will read later. I think in the course at the last phase you will be reading the testing of the chip. Oh, some more are there. Okay, that I think these are all same. You will be using that thing. That what is the logic synthesis? Mainly the CAD tools will be doing. You have nothing to do. Minimize number of gates, levels, and activity. Something I have written for this library. Actually, I used many times this library. So later you see what is there. Target and link library. Particularly, I have given because for the in the lab you will face problem sometimes. So what to link, etc. I have given. You read that later. And this is actually the technology mapping, that library, the what type of, for this library what gates are available, and for the delay power. These are the verification.